Good evening, students. So let us continue the discussion on the nuclear reaction. So in the last class, I've explained the concept of the nuclear chain reactions, how the reactions is going to take place. And we have explained the concept of the nuclear fission, the reaction, how the energy is going to be released. In the case of the nuclear fission, we are going to consider a heavy nuclei. Heavy nuclei means mass number will be more. So heavy mass like 92 uranium 235. When this uranium is going to be bombarded with a neutron, it is going to be formed with uranium 236. This uranium 236 is going to split into two parts like barium 141 and krypton 92. This heavy nucleus split into two parts is what we consider as the nuclear fission. And you can observe here, always the neutrons is going to be released. So in each and every nuclear fission reaction, the neutrons has to be released. In this nuclear fission, almost the energy released is about 200 mega electron volt. So depending upon the number of neutrons which is produced in each reaction, depending on that, we are introducing one more important parameter that is called the multiplication factor, or you can also call it as a reproduction factor. Multiplication factor, or also you can consider as a reproduction factor. Now, in the case of a multiplication factor, we are going to determine this factor by knowing the number of ions in the previous generation to the number of neutrons in the present generation. So number of neutrons, by knowing the number of neutrons in the present and in the past generation, we are going to detect the multiplication factor K. Suppose if the multiplication factor K is equal to 1 in each and every reaction, the number of neutrons will be the same. Number of neutrons will be the same. Please remember this. Number of neutrons will be same in each and every reaction. So whatever the number of neutrons present in the present generation, that will be same as the number of neutrons present in the previous generation. In such case, we are going to consider as the chain reaction as a steady state. When the nuclear reaction is said to be a steady reaction, if the number of neutrons present in each reactions are same, then we are going to say that it is a steady reaction. And the size of the fissionable material is used to be a critical size under this condition. So when the nuclear reaction is a steady, then whatever the size and the mass we have in the nucleus, that corresponding size we call it as a critical size, and the corresponding mass we call it as the critical mass. If K value is more than 1, then we are going to say that the nuclear chain reaction accelerates. So where the number of neutrons in the present generation is more than the number of neutrons in the previous generation. So number of neutrons will be more in the present generation comparatively to know the number of neutrons in the previous generation. So number of neutrons is more in the present generation compared to the previous generation. Then we are going to say that the value of K is 1. Then the reaction is said to be an accelerate reaction, where the reaction can also have a chance of explosion. The reaction may get explode and it releases enormous amount of energy. In this reaction, in this case, whatever the size or the mass we have, that is called a supercritical size. Then, if the K value is less than 1, that clearly tells the number of neutrons in the present generation is less compared to the number of neutrons in the previous generation. In such case, the chain reaction gradually comes to halt where it slowly decreases. In this case, whatever the size of the material we have, that is said to be a subcritical size. So this is what exactly we are going to say for steady state, for supercritical, and for subcritical, depending upon the value of K. Yes. Coming to the nuclear fusion. In the case of the nuclear fusion reaction, here we are going to consider the light nuclei. We are considering a two or more than two light nuclei. This light nuclei is going to be combined to form a heavy nucleus. To form a heavy nucleus, we are going to combine into a single nuclei. That is what we call as the nuclear fusion. For example, here we are going to take a deuterium, 1H2, 1H2. 2 deuterium is going to combine to form a helium nucleus, 2He4. So whatever the helium nuclei is formed over here, when the two deuterium are combined, this is what we call as the nuclear fusion. But please remember, this nuclear fusion reaction is going to release an energy of about 24 mega electron volt. What is the energy released in the nuclear fusion reaction? 24 mega electron volt. But what is the energy produced in the nuclear fission reaction? In the nuclear fission reaction, the amount of energy released is 200 mega electron volt. Clear? Yeah. So please remember, in the case of a nuclear fusion, energy released is about 200 mega electron volt. But if you calculate the specific binding energy for nucleon, it is less. But in the case of the nuclear fusion, binding energy is approximately 20 mega electron volt. But if you calculate the specific binding energy, that specific binding energy will be very high in the case of a nuclear fusion reaction. So there will be two cases, nuclear fission and the nuclear fusion. So please remember the energy released in both the cases. And I think you know how to calculate the binding energy, right? You know how the binding energy is calculated. Binding energy is calculated by using the formula mass defect into 931 mega electron volt. You have to be at least remember how to find the binding energy for standard nuclei, like for 7 and 14, for helium nuclei 2He4, and for oxygen nuclei 8O16. For this, you must know how to calculate the binding energy and also the specific binding energy. When we are taking the problems, you can come to know all those things, how we are calculating the binding energy, specific binding energy for a given nuclei and all those things. Yeah. Now, before going to the radioactivity, let me finish some few questions based on nuclei. Then I will pass on to the radioactivity concept. You know that radioactivity means the splitting up of the nuclei into heavy nuclei into two or more light nuclei. When this process is undergoing, there will be an emission of radiation. That phenomenon is what we called as the radioactivity. Yeah. Look at this. A heavy nucleus at rest breaks into two fragments where velocities are in the ratio 8:1. What is the ratio of the radii of the fragment? Actually, student, this problem was asked recently in the 2 days before JEE exam. Same concept. I think the number is 4:1 or 5:1. Yeah. What is the velocity ratio, students? What they have given? Velocities of the two particles are in the ratio V1 by V2 is 8/1. Now they are expecting you to find the ratio of the radii. The ratio of the radii, that is R1 by R2. Ratio of the radii, that is R1 by R2. Yeah. Now you know that whenever the nuclei is going to break into two parts, according to the conservation of momentum, initial momentum is equal to the final momentum. Correct? No? Initial momentum is equal to the final momentum. Since this mass initially at rest, the initial velocity will be 0. If initial velocity is 0, the initial momentum must be 0. Initial momentum must be 0. Now this is going to split into two parts, m1 v1, m2 v2. So this should be m1 v1 plus m2 v2. According to the conservation, 0 must be equal to m1 v1 plus m2 v2. You shift this term to this side. So minus m1 v1 is equal to m2 v2. Or you can tell v1 by v2 is equal to minus m2 by m1. This negative sign only it indicates the two particles after disintegration are moving in the opposite directions. So v1 by v2 is equal to m2 by m1. What is mass? Here mass number is represented with a2 by a1. So what is here represents? Mass number. So m2 by m1 is going to be replaced with a mass number in the case of a nuclei. In the case of a nuclei. Now, in the case of the property of a nuclei, we have given the formula for the radius for the nuclei, which is given by the formula r is equal to r0 into a power 1 by 3, isn't it? So what is r1 by r2, students? What is r1 by r2? R1 by R2 will be something like R0 by R0, that is going to get cancelled out. So it will be A1 by A2 whole power 1 by 3. Clear? So R1 by R2 is equal to, what is A1 by A2? V1 by V2 is A2 by A1. A2 by A1 is V1 by V2. So what is A1 by A2 then? Make it reverse. So it becomes V2 by V1. Whole power 1 by 3. What is V2 by V1? V2 value is 1. V1 value is 8. Look at this. V1 by V2 is 8 by 1. But we are doing V2 by V1. So it is 1 by 8. Whole power 1 by 3. So what is 1 by 8 whole power 1 by 3? It is 1 by 2, that is cube root of 8 is 2. So it is 1 by 2. So if the velocity is in the ratio 8 is to 1, remember the radius must be in the ratio 1 is to 2. 1 is to 2. So which is the right option? Option A. Clear? Yeah. You can look at the second question, which is very quite simple. The ratio of the radii of nuclei. One nuclei they have given as 13 aluminium 27. Second one they have given as 52 beryllium 125. What is the radius ratio? What is the mass number of the first nuclei? 27. What is the mass number of the second nuclei? 125. So you know that radius is directly proportional to a power 1 by 3. If radius is directly proportional to a power 1 by 3, you know that the radii is directly proportional to mass number. So what is R1 by R2 then? R1 by R2 will be equal to A1 by A2 whole power 1 by 3. R1 by R2 is equal to A1 by A2 whole power 1 by 3. So A1 is 27 by 125 whole power 1 by 3. What is the cube root of 27? You know that cube root of 27 is 3. Cube root of 125 is 5. So what is the radius ratio? R1 by R2 ratio? 3:5. 3 by 5. 3 by 5 can also be taken as 6 by 10, no? Multiply and divide by 2. So you are going to get approximately the option A, 6:10. This 6:10 also can be taken as 3:5. 3:5. Yeah. Now, they have given the nucleus of 92 uranium-235. For this 92 uranium-235, it is undergoing a fission. In this, 0.1% of the original mass is converted into energy. What is the original mass? 1 kg of this uranium-235. Now, you know that mass is interconvertible into energy. Mass and energy are interconvertible. So how to calculate the energy? Energy can be calculated if you know the mass in kg. Mass in kg, you can express the energy formula in terms of E is equal to mc square. So mass is 1 kg, but we have not taken complete mass, but we have taken only 0.1% of that 1 kg. What is 0.1% of 1 kg? 0.1% means 0.1 by 100 into 0.1 by 100 into 1 kg. 0.1% of 1 kg. This is mass. Into c squared. What is c squared? C value is 3 into 10 power 8 whole square. C value is 3 into 10 power 8 whole squared. So this is 0.1 by 100 is 1 by 1000 into 3 squared is 9. 10 power 8 into 2 will be 16. So this implies 9 into 10 power 13 joule. So what is the energy stored? 9 into 10 power 13 joule. The same value can also be expressed in electron volt. If you want to find the energy value in electron volt, then you have to take the value of energy in electron volt just by dividing 1.6 into 10 power minus 19. So if you just divide by 1.6 into 10 power minus 19, this joule is converted into an electron volt. So if you just divide by this 3 by 2, 18 by 9, approximately this 9 by 1.6 is 6. Into 10 power, when minus 19 comes up, it will be plus 19. Plus 19 plus 13 will be 6 electron volt. So this is the energy in electron volt. So the same value, instead of expressing in terms of joule, they may express in terms of electron volt also. But remember, if the mass is in kg, then only we are using this formula E is equal to mc squared. If mass is in AMU, if mass is in AMU, then you have to make use of energy as delta M into 931, and this value will be in terms of mega electron volt. Energy will be equal to in terms of delta M into 931 mega electron volt. Please remember, this is the energy. These are the 3 different formulas while calculating the energy. Yeah. Come to this problem. 1 gram of hydrogen is converted into this 0.993. Initially, we have a mass of 1 gram, initial mass. This is converted into 0.993 gram of helium. This is hydrogen. and this is an helium. Then what is the energy released? Students, you can consider this as the final mass. You can clearly convert this gram in terms of kg, right? Yeah. Since the mass is in kg, how to calculate the energy? Energy is calculated by using what? Delta M, that is mass difference, into C square. Into C squared. Then what is the mass delta M? Delta M is nothing but what? Delta M is nothing but the change in mass. So what is the change in mass? How to calculate the change in mass? 1 gram minus 0.993. This is how much? 0.007. Correct, no? Can you calculate what is the energy now? You know the value of delta M. You know the value of delta M multiplied by C square. How much you'll get? Yeah, delta M is 0.007, right? Into C squared upper, that is 3 into 10 power 8 square. So 0.007, 3 squared will be 9 into 10 power 16. 9 into 7 will be 63 into 10 power 19, right? This is 0.007 into 9. How much you'll get? 0.007 or you can take this as 7 into 10 power minus 3 into 9 into 10 power 16. Yeah, this is in gram, right? This is in gram, right? So you have to convert that gram into what? Kg, right? You have not converted the mass in terms of kg. Convert that mass in terms of kg. 0.007 into 10 power minus 3. Why 10 power minus 3? To convert into kg. So 3 squared will be 9 into 10 power 16. So 0.007 can be taken as 7 into 10 power minus 3. This 10 power minus 3 as it is into 9 into 10 power 16. So this value will be equal to 7 into 9 will be 63 into 10 power minus 3 minus 3 minus 10. Minus 10 plus 16 will be plus 10 joule. So this is the value of the energy released in the reaction. So 63 into 10 power 10. 63 into 10 power 10 joule. So option B is the right answer. What exactly the mistake we did here? We have not converted that gram in terms of kg here. Just we have missed that 10 power minus 3. So 63 into 10 power 10 joules. Suppose if they are asking you to convert this same value in terms of electron volt, what you are doing? If you want to convert the same value into electron volt, you are just going to divide by 1.6 into 10 power minus 19. When you divide this value by 1.6 into 10 power minus 19, you are going to get in terms of electron volt. Yeah. Look at the question here. The masses of the neutron and proton is given. Mass of the neutron. Shall I use Mn? Mn represent mass of the neutron. That is 1.0087 AMU. You know AMU is nothing but atomic mass unit. AMU is nothing but an atomic mass unit. And what is the mass of the neutron? Proton mass is also given. Mass of the proton is 1.0073 AMU. And they're telling that the neutrons and protons are combined to form a helium nucleus. Proton and neutron mass are going to form a helium nucleus. So neutron means what? 0N1 plus proton means 1H1. This is going to form with the helium nucleus. What is helium nucleus? Please remember, helium nucleus is alpha particle, which is nothing but 2He4. 2He4. So neutron and proton are combined to form a helium nuclei, that is 2He4. Now you just balance this equation, students. You just balance this equation. We have mass number 4 here, but we have total mass number is 1 and 1 here. So I'll take this as 2. Then it will be 2 into 1 will be 2. Still 4 is there. So I will also multiply it with the 2 here. So 2 into 1 plus 2 into 1. That will be 4. 2 into 1, 2. Here 2 into 0 will be 0. So to balance the equation, you have to multiply 2 in the reactant side. So instead of taking 1 neutron and 1 proton, you have to take the 2 protons and 2 neutrons to form a helium nuclei. For this, they're asking you to find the binding energy. Yes, what is the formula for binding energy? Binding energy is given by delta M into C squared. Don't use C squared here. Can you tell me, students, why I am not going to use C squared? Because the mass is not represented in kg. Mass is not used in kg. So that mass is there in terms of AMU. So you can directly take this as into 931, but you have to write the unit in mega electron volt, not in joule. So what is the formula we have for the binding energy? Binding energy is delta M into 931 mega electron volt. But how to calculate this delta M, students? This delta M can be calculated as mass of the reactant difference mass of the product. Mass of the reactant minus mass of the product gives the mass defect delta M. So how to calculate the mass of the reactant? So mass of the reactant. On the reactant, we have 2 times of neutron. 2 times of neutron. Neutron mass is 1.0087 plus 2 times of the protons, that is 1.0073. So mass of the reactant is equal to, if you simplify this, two into 1.0087, you will get 2.0174 plus 2 into 1.0073. It is almost 2.0146. So this mass of the reactant is equal to 2.0146 plus 2.0174. that is approximately you're going to get 4.032 AMU. This is mass of the reactant. Therefore, in the product, we have a helium nucleus. So delta M is nothing but mass of the reactant minus mass of the product. What is the mass of the reactant? Mass of the reactant 4.032 minus mass of the alpha particle is 4.0015. If you take that 4.0015, you'll get it as 0.0305. Mass of the reactant is 4.032 minus mass of the product is 4.0015, because product here is helium nuclei. Here you have to consider the helium mass 4.0015, that is 0.0305. So this is delta M, mass defect. Once if you know the mass defect, you can find what is the binding energy. You know how to find out the binding energy. That is delta M into 931 mega electron volt. You know that delta M is 0.0305 into 931, which is equal to how much? If you multiply that with 931, approximately you are going to get 28.39 or 28.4 mega electron volt. So you can go with option A, that is 28.4 mega electron volt. Yeah. Come to this. Atomic power reactor is there. Student, once again, before going to this, for the same problem, they may ask you to find. For the same problem, they may ask you to find binding energy and specific binding energy of alpha particle. Instead of giving like neutron is combined to form proton, everything, they may ask the question like this: find binding energy and specific binding energy of alpha particle. What is alpha particle? You know that it is 2He4. And they will give what is mass of the proton, that is 1.0073. And also they will give mass of the neutron, that is 1.0087. Addition to this, they will give mass of the alpha particle. Mass of the alpha particle, that is 4.0015. All these masses are in AMU, no doubt. So here they won't ask that the 2 protons or 2 neutrons are combined everything. No. Instead of asking that neutrons and protons are combined to form that, instead of that, they may just ask you to tell, just you find what is binding energy and the specific binding energy of the alpha particle. Just they will mention only alpha particle. They won't tell that neutron is combined to form proton or proton is combined to form a neutron. In such cases, you have to find only if the nuclei is given. Just you find out what is the value of Z. Z value is 2. What is mass number A? 4. By knowing the Z value and mass number A, you have to find delta M. Yes, students, how to find the mass defect if you know the Z number and atomic number and mass number? Yes, delta M is given by the formula ZMP plus A minus Z into Mn minus M dash. ZMP plus A minus Z into Mn minus M dash. M dash means the actual mass of the alpha particle. So what is Z value? Z value is 2. So 2 times of the mass of the proton. Mass of the proton, you got it as 1.0073 plus A minus Z. A minus Z is 4 minus 2. That is 2 neutrons. That you will get 1.0087 minus mass of the alpha particle, that is 4.0015. This is same as what you have calculated in the previous problem. Here, 2 proton mass, 2 neutron mass, you will get 4.032. So if you add these two, you will get 4 point, that value, you got it as 4.032. So 4.032 minus 4.0015. You calculate this delta M. After getting this delta M, just multiply 931. This you will get 28.4 mega electron volt. So the question was asked in the reaction form, like 2 protons and 2 neutrons are combined to form a helium nuclei, that is alpha particle. So instead of giving the reaction type, they may ask directly to find what is the binding energy and specific binding energy of alpha particle. Just by knowing the atomic number here and the mass number, by knowing atomic number and the mass number, you can find what is the binding energy. Suppose if they are asking you to find the specific binding energy. So this is no doubt you will get 0.0305. After this, you are going to get binding energy, that is, you will get 28.4 mega electron volt. For the same problem, they are also expecting you to find the specific binding energy. You know that the specific binding energy is given by the formula binding energy divided by the mass number. Binding energy divided by the mass number A. So specific binding energy is equal to what? Binding energy divided by the mass number. So for 28.4, you have to just multiply the mass number, that is 4. So 28.4 divided by 4. This value is what we called as the specific binding energy. So students, you have to be very careful if they are asking you to find the binding energy and specific binding energy of the given nuclei like 2He4. Similarly, they may ask the others different types like 7 and 14, and they will ask 8 or 16. Anyway, mass of the proton and mass of the neutron will be the same. Just you have to change the value of the actual mass of the nuclei. For alpha particle, it is 4 point something. Similarly, for nitrogen, it is 14 point something. And for oxygen, it is 16 point something. So by knowing those masses, you can find the binding energy or the specific binding energy in the same method. Clear? Yeah. Now you can take up this problem. What they have given, there is an atomic power reactor. You know that atomic power reactor will produce us a nuclear energy, and that is delivering 300 megawatt. 300 megawatt means that is power. What is the power they have given? 300 megawatt. So power is equal to 300. What is mega? Mega means 10 power 6 watt. What is the energy released for the fission of each uranium atom? 170. 170 for uranium-238. For uranium-238, the energy released is 170 mega electron volt. 170, what is mega? Mega means 10 power 6. How to convert this electron volt to joule? Just by multiplying with 1.6 into 10 power minus 19. So 170 into 1.6. 170 into 1.6. That is how much? 272 into 10 power 6 minus 19 is minus 13. This is in terms of joule. So this is the energy released. Now they are asking you to find mass of, they are asking number of uranium atoms fissioned per hour. So what is the time they have given? Per hour. For 1 hour they are expecting. For 1 hour they are expecting. Yeah. Just note down here. You know the power is given by the formula energy by time. Power is nothing but what? Energy by time. If there are n number of atoms of fission, then n into E by T. And they're asking you to find the number of fission only. So number of fission is given by the formula power into time divided by the energy. Power into time divided by the energy. So n is equal to, what is power? Power is 300 into 10 power 6 watt. Time is 1 hour. For 1 hour, you know that 1 hour, how many seconds? 3,600 seconds, right? So 1 hour equals to how many minutes? 1 hour is 60 minutes. 1 minute is 60 seconds. So 60 into 60 time. Whole thing divided by the energy. What is energy you got? You got 272, right? 272 into how much? 10 power minus 13, right? 10 power minus 13. So n is equal to, so you can count zeros, 2 zeros, 3 zeros, 4 zeros. So you just take 3 into 6 into 6 into 10 power, this 4 zeros plus 6, 10 power 10. Whole thing divided by 272. This is equal to, what is 3 into 6 into 6? 3 into 6 will be 18, right? Into 6, you will get almost 108. 108 divided by 272 into 10 power, this is 10. I'll keep this 10 power minus 13 as it is. If I shift 10 power minus 13 to the numerator, it becomes totally 10 power 23. 10 power 23. Yeah. So what is 108 divided by 272? 108 divided by 272 is 0.397 into 10 power 23, or approximately I can take it as 39.7 into 10 power 21. So 39.7 means approximately you are going to get how much? You can cross check that. 39.7 is how much? So you can take option C. No, it is close to 40. So 40 into 10 power 21. So this is how we are going to calculate the number of uranium atoms which is fissioned per hour. So here also we got it as same, that is 40 into 10 power 21 atoms. This number of atoms are going to be released in 1 hour. In 1 hour. So this is the simple problem by giving the power in the case of the reaction time. Yeah. I think the next PDF is not copied here. Still the problems are there in the Nuclei, students. Still, the 3 to 4 problems are there based on calculation of fission energy in the reaction types. How the energy is released in nuclear fission, nuclear fusion. That PDF is not attached over here. Those questions is not attached. Okay. So that I will take up that problems in the next class only. After calculating all those 4 to 5 problems, then we'll jump into a radioactivity. But radioactivity is simple concept. How the nuclei is going to disintegrate, while disintegrating, how the energy is going to be formed, how the energy is released in the reaction. All that things we are going to analyze in the case of the radioactivity. In that radioactivity also we are going to analyze the 2 important concepts, students, that is the half-life and the number of atoms decayed, which you call it as a radioactive decay law. Radioactive decay law. Those 2 concepts we are analyzing, and we are going to solve the problems based on the activity also. So another 2 to 3 sessions is required to complete this nuclei chapter. Then we're remaining with the last chapter, that is semiconductors, which is a theory concepts, which we can go ahead fast so that we can complete that. So that I will continue the problems of nuclei and radioactivity in the next session, students. Fine? Yeah. Thank you.